Hi, my name is Karthik. I'm head of streaming at Databricks. The title of my talk is Project Lightspeed Goes Hyperspeed. Essentially, Project Lightspeed advances Spark Structured Streaming into the new age of streaming. Um, so let's delve into more. So new opportunities in real time that are emerging. So every organization generates a lot of real time data these days. I mean, banks generate retail transactions, and retailers generate point of sale data. Then airline reservations generate a lot of data in terms of reservations and cancellations, and telecoms generate call center records. Similarly, on the web, there are a lot of interaction using web clicks and social posts, email, instant messages, and the third party generate a lot of news feeds, weather data, market data, real time traffic, which are incorporated into decision making. IoT events generate a lot of sensor data, geolocation data, and machine logs, and mobile devices generate another set of events. So all these data generated across the enterprise is creating a lot of opportunities for new real-time applications that includes fraud detections among the transactions that you done in a credit card, putting a personalized offer when you're browsing a social site or web purchasing, vaccine distribution, where the inventory is and where the inventory is low, and how to distribute it quickly. Smart pricing for electricity based on the grid is getting input versus where it's can be consumed. Then predictive maintenance, where you can, if your PC is continuously being monitored, and we can see whether the hard disk is going to go down or not, and immediately send a replacement before it even fails. So these are a lot of new opportunities in real time. Databricks leads streaming. Why? Databricks is built on a very popular stack based on Apache Spark. It's Apache Spark Structured Streaming. We have more than 36 million downloads per month. And the key reason why Apache Spark Structured Streaming has been adopted across the board is it's a unified engine for batch and streaming. So once a team has learned about the APIs, the same API is applicable for streaming, and all you have to do is change the trigger mode to continuous, and the batch job becomes a streaming job. It's as easy as that. And it's fault tolerance. Streaming systems can be um, bifurcated into pessimistic systems as well as optimistic systems. Pessimistic system means every stage is checkpointed. So Spark belongs to a pessimistic system where every micro batch is processed, and the checkpoint is stored in the distributed storage, and before the next batch resumes, next batch is scheduled. So that way, like, your failure is restricted to the last batch that failed. So it provides low latency and cost effective, because of the trade-off based on the number of slots that you provide for scheduling. So if you have you want low latency, you should have slots equal to the number of tasks that you are going to schedule. If you want to cost, you can have reduced slots and more tasks, and it'll crunch through the other available slots, and you can trade off between cost versus latency. And easy to use and powerful operators that includes arbitrary stateful powerful processing, as well as slew of operators including stream join, windowing operators, and platinum group with state, and for each batch. So this is one of the main reasons why Apache Spark is adopted widely. And streaming is bigger at Databricks. There are a lot of millions and millions of jobs run every day. So we are running around 18 million jobs and shows the growth over from 2019. And we started Project Lightspeed a couple of years ago to advance Spark Structured Streaming into the new age of streaming. So we are going to take a couple of items that we delivered as a Project Lightspeed. One is called stream pipelining. So essentially, ETL can be done on using stream pipelining in DLT serverless. And what are we doing for low latency operational use cases with the new Databricks capabilities? And also, arbitrary stateful processing is getting a new API transformer state with very rich functionality. Now let us look at the first streaming ETL on DLT serverless stream pipelining. So one of the thing that we wanted to touch upon is how fast we can ingest data from into Lakehouse. So in order to find out how we are doing, so we did a benchmark, and so we use Delta Live Tables, which is a abstraction that is built on top of Spark Structured Streaming and the serverless version of it. It's a declarative pipelining framework in Databricks data intelligence platform. With serverless simplifies operation burden, no more cluster management and adding more nodes to the cluster, removing nodes from the cluster. Just available. Just launch your job, it will figure out on its own what to do. And uses Photon Engine by default. Photon Engine is a fastest Spark engine that we developed in-house using C++, and it supports a feature called stream pipelining, where microbatches are scheduled as soon as the slots, consecutive microbatches are scheduled when the slots are available. We don't have to wait until one microbatch completes all the tasks. If there's some of the slots of the previous microbatches are available, the next microbatch tasks are scheduled. And jobs computing for Spark Structured Streaming. It is a traditional compute offering from Databricks, where you need to get a cluster in the customer cloud, and which is managed by Databricks, but customer has to create, know what type of instance to create, and give it to Databricks to ask the Databricks to create it and manage it. And it uses Photon for the evaluation. Other open source options, many options are available, including Apache Flink and custom raster writer into Lakehouse. We use Apache Flink from a major cloud service provider for for this evaluation. So how to do benchmark flow? So we take data from Kafka and write it into Delta Lake and see how fast we can go. So data is pre-populated in Kafka by generating explicitly, and the streaming engine, which is a Spark streaming engine, or a DLT, which is built on top of Spark, deserializes JSON string, projects the incoming data into a strongly typed data structure, and presses the data into a Delta table in the Lakehouse. And then this is the ingestion part of it. Now, how effective ingestion is, that will be known when you can query the Delta table. So that's the second part of it. Run queries against the Delta table that you ingested right now. So what we measured. So first we measured is how long does it take to drain the data out of Kafka into a Delta table There's a happy path. We assume there's no node failures, and how long it takes. And failures are common in cloud systems, so we need to be practical. So which means we also did take down a couple of nodes during the benchmark, and we measure the impact of node loss in terms of how long does it take to ingest. Once the data is ingested into the Delta table, we run a bunch of different queries on the Delta table to figure out how effective ingestion is. So now let us look at the results. So results, as you can see, DLT serverless is fastest with The DLT with serverless compute is faster with 3,865 seconds, and the jobs compute is 4,980 seconds. Whereas Flink with 10 seconds checkpoint interval and 20-second checkpoint interval took more time. So DLT is 29 faster than the classic compute and 63% faster than Flink. This is in the regular happy path. Now let us look at the ingestion failures. So DLT with serverless just increases by 8%, whereas Jobs Classic increases just by 13% to 5,662 seconds, whereas it's much more than 35% for Flink on both the checkpoint intervals. So that clearly shows how the microbatch pessimistic checkpointing helps a lot so that you don't have to recover from a previous checkpoint like Flink does. Where here you just have to replay the previous microbatch. So read performance. We did a bunch of queries, including simple count query and a simple point query to select a particular data, simple range query, simple nested query, then simple nested match query, a simple aggregate query, different queries essentially. And as you can see, a simple count query ingested using DLT and Jobs Classic, that essentially Databricks offerings, are much faster than the open source Flink Delta writers. So this is because the way we write Parquet is very different from the way open source Parquet written by Flink and others. That's what makes it much faster. The stream pipelining, the reason why we are doing faster with DLT as well as Apache DLT serverless compute is because of the stream pipelining. Stream pipelining essentially overlaps stages of different microbatches as soon as the slots are available, and improves the performance by 3x and reduces the latency by 30%, and works for all streaming queries in serverless. So, which is why serverless is much faster than Jobs Classic. Now, let us see the low latency operational use cases. So, there are several operational use cases that you encountered. So, such as how many active logins do I have for a streaming account? What are my operators of industrial equipment? Do I need to send a proposition to users struggling to purchase? So business critical operational use cases need consistently low latency. Even though Spark gives a low latency, we need a much more lower latency since customers are requesting for it. So we announced recently real-time mode, which is essentially another type of trigger. You just simply flip a switch and it works with no code changes. All the code, it just becomes enable low latency. Under the covers, it computes the logic for the pipeline seamlessly. And this is available in private preview in the second half of 2024. Now, how fast were we? P50 is tens of milliseconds and P99 is 100 to 200 milliseconds for some of the queries that you benchmark. So the stateless stream static join is reduced to 43 milliseconds, and the stateless transformations, ETL kind of transformations, come down from 6x to 50 milliseconds, and stateful simple aggregation came from 10x to 187 milliseconds, and the dedupe queries become much faster with 223 milliseconds, and stateful stream static join plus aggregation came to 185 milliseconds. So how did you do it? So before do it, let us look at the latency spectrum. Streaming ingestion and ETL operate in a few seconds to minutes, like 3 seconds and upwards. Whereas the operational use cases start from 10 or 20 milliseconds and go up to seconds. So the micromatch mode that we have cooperates around up 1 second onwards, which is satisfies streaming, ingestion, and ETL use cases. For operational use cases, we can we use the real time mode that gives a latency of anything around 10 to 20 milliseconds all the way to under 200 milliseconds. So that's why like we divide the latency spectrum into ultra real time, 1 second, multiple seconds, multiple minutes, and with the real time mode, we can capture the entire spectrum of applications. How did you do it to get the real time mode provide latency in the milliseconds? So we measure the microbatches and found out some of the microbatch overheads and made the microbatch to run a little longer as time-based microbatch as compared to a record-based microbatch. So we run the microbatch for 5 minutes to few 6 or 7 minutes and schedule all the mappers and reducers in one go. For a Spark microbatch, it will schedule the mappers first, writes into the shuffle area, and read from the shuffle, and then schedule the reducers and read from the shuffle and process the data. Whereas here we schedule the mappers and reducers in one go, and we ensure that the resources are available for it, and connected the mappers and reducers with the streaming shuffle. This shuffle does not go to disk. As the mappers keep writing into the shuffle, shuffle delivers the data immediately to the reducers and makes the data available to downstream operations immediately after generations. With a simple trick and a few changes in the operator, then we are able to achieve this low latency. Now let us look at the arbitrary stateful processing in streaming. Stateful processing is one of the important area of stream processing that has a lot of applications, and is very important for operational use cases as well. So state is something like information maintained for future use, updated by tasks, Spark tasks in memory, and which is stored in DocsDB that is backed by distributed storage. Version the state checkpoint is version within macrobatches. So stateful stream query essentially combine multiple records together. Different type of stateful operators are there. Both predefined operators and arbitrary stateful operators. Predefined logic has built-in operators like window aggregation, like tumbling window, session window, etc. Even join includes a stream static join and stream join, deduplication. Arbitrary logic operators provides the per key user-defined operators and specialized APIs like platform group with state and map group with state. Now, so currently we support platform group with state, which is essentially a user UDF for arbitrary state processing. So essentially, state interactions are managed by a grouping key and taking the state corresponding to the grouping key. As you can see, it's grouped by the credit card ID, and then you can define a function which reads the state for that key, compute average, and save it back to the state. So that's what the Platinum group with states provides. Now, what are the limitations of Platinum group state? Lack of composite types. So values stored in group state types are single scalars, and we cannot support data structures like list, map, etc. efficiently. Current approach requires users to read the entire state, deserialize it, manipulate it, and serialize it back again. And the lack of data modeling functionality for state. So you cannot split the state for a grouping key into multiple logical instances, which can be read and updated independently. So that's why we introduced state variables. No granular eviction control. In other words, we cannot support eviction based on some timers or per state variable eviction, and no schema evaluation for the state. So once the schema is set, we cannot evolve the schema as a business requirement changes over a period of time. So we need a layered, flexible, and extensible stateful processing. So that's what we introduced. Introducing transformer state, user-defined arbitrary stateful processing with a layered API. So transformer state takes a stateful processor, which consists of a handle, which in turn can support composite types and state timers, metadata, and provides an underlying every state is implemented using RocksDB, which is a state store provider. For example, let's take a credit card fraud detection. So you read a stream from a table called transaction bonds table with watermark, and you can do a transform state, and you give a new fraud detection processor, and what is the time that you want to give, whether event time or processing time, and what is the output mode that you wanted to um, specify. So now the fraud detection processor is something that a programmer can write. So it extends the stateful processor and get the list state, because all the transactions are stored as a list for a particular card ID, which is a group in terms of the recent transactions. Get the value state for the maximum transaction, and handle the rows, in the sense like process the rows based on the event occurred. So if the timers expire on this thing, then you can handle the rows, handle input rows is called for the expired timer, and process the timer callbacks. So now on the composite data types that we support value state, list state, map state. The advantages include flexibility in data modeling, optimized read writes. We don't have to bring the bigger, if the state corresponding to a group ID or a key group ID is pretty big, you can bring selectively the state. So append list without read update, right? Efficient key value access for map state, and allows and adding and removing state variables for a query within the same checkpoint location. State timers, flexible and extensible approach to expiring state. Support for event time and processing time-based timers. Expire timers triggered in the earliest available macro batch. Timers are stored durably and maintained across job restarts. Multiple timers per grouping key can be supported, and timers are deduplicated for the same timestamp. Operator chaining. So we can have one transform state feeding to another transform states, so that in a single query, then you have to define event time column, which will be emitted from the stateful operator, and that allows chaining. So even more functionality. We can even set a state TTL, and the state will be automatically cleaned up. State initialization. You can initialize the state from an existing query or a Spark dataset. Enables you to use an existing state. Schema evaluation. Define the state using Scala case classes or POJOs. Modify case class schema as long as compatible with the existing systems schema. Where are we going next? Project Lightspeed goes ludicrous speed or flight speed. We listen to our customer constantly. Directionally, this is what they are telling us. Catered performance features per use case. State features like the repartitioning, checkpoint CRUD operations for manipulating the state, complex event processing support, and expanding DLT use cases, and add additional things for operational use cases like key value stores, like such as Aerospike. We need to add connectors, and then for OLTP databases and also message bus systems. Support for multiple syncs and fan out, and hybrid batch and data sources. Thanks for listening. That's all.